begin today's class with bilinear forms. Okay. So, as the name already suggests, it is about a form which has two variables or two arguments, okay, and it's linear in both of the arguments. So earlier we have seen linear transformation, which took input of one vector and it was linear in that variable, right? And that variable means that vector, okay. And here now, suppose you are having a vector over some field f. So we are considering now a map from V cross V to F. Okay. Give it some name S. Later we will denote it by just by two brackets, but for the moment, since we are talking about a map, give it some name S. Okay. So what are the properties that we require? We require S to be linear in both of its arguments. Okay. That means you have S of, say, some multiple from C from F. So C times V and W. This will be just C times S V W. Okay. And S of V1 plus V2, two vectors from V, another vector W from V. This would be just S of V1 W plus S of V2 W. Okay. And the same for the second variable as well. Okay. So now then can you tell me how many terms this will have? Very nice, 4. This is S V1 W1 plus S V2 W2 and also S V1 W2 plus, excuse me, please write your name, S V2 W1. Okay. So indeed, as you guessed, if it is also bilinear, so this, so similarly in the second argument. Okay, that is, if you multiply the second argument with the scalar comes out. If you take W1 plus W2 instead the second argument, it will be a sum of the first argument times W1 plus S of V1 plus V2 W2. Okay, and then you expand this, you get all these 4 terms. Okay. More precisely, you can write this, that the properties, okay, bilinearity of S you can also write it as S of summation AI VI I and say summation over J Bj Wj. This will come out to be what? So you have a finite sum over this, say I is running from 1 to n, say j is running from 1 to m. Okay. Summation, yeah, summation I running from 1 to n, yes, j running from 1 to m, yes, ai times bj vi wj. Okay. So this follows from the bilinearity because it's linear in the first variable as well as, or first argument as well as the second argument. Okay. So any sum here decomposes as the sum of the individual summands. Okay. And the same happens here. So if you have two sums here and here, it is just a double summation there, and then the scalars, corresponding scalars are multiplied. Okay. Ah, right, here it will be an S here. Thank you. The ordering, it's a finite sum. So it doesn't matter in which way you sum it. A bilinear transformation, yes, maps from V to V to the scalars. Sure. Have you seen something like this earlier? Yes, which one? Determinant, well, yeah, right, but determinant is determinant from where to where? Right. So in general, determinant is a multilinear form. Okay, so it's even a more general thing than this. Okay, here we are talking about 2 arguments, and determinant takes n arguments in it. It's an n cross n matrix. Take all the rows or all the columns. Okay, and then the determinant is linear in each of the columns or each of the rows as you view it. I mean, if you can see it as a function of the rows of an n cross n matrix or function of the columns. Sorry, function of the columns of an n cross n matrix. Okay, and this is linear in all of them. So in particular, if you are considering a 2 cross 2 thing, bilinear form, then you should consider a matrix, a 2 cross 2 matrix, and then it is linear in both of its columns or both of its rows. Okay. So indeed, the first example is from R2 cross R2 or C2 cross C2 or some F2 cross F2, determinant is a map. Okay. And then, actually I didn't expect this to be the first example. Okay. Exactly. Yeah. Okay. But that's very nice that you have already observed that determinant is a bilinear form. Okay. Determinant of on the 2 cross 2 things. Okay. Now, the second is the dot product. Okay. So actually, we'll often denote this instead of using some function like, something like this, we will often use just brackets like this, a less than, a greater than, angular brackets. Okay. Instead of S, we will write often this one. In particular, when we denote dot products, we'll definitely use this notation. Okay. So this one, which is taking in 2 variables here, from Fn cross Fn to F for an arbitrary field, this also defines a bilinear form because it is bilinear in both of the variables. Okay. And how do you define the dot product on Fn cross Fn? So let's recall dot product from Fn cross Fn to F, and here suppose you have 2 vectors, say x, some column vector in Fn. How do you define this? Yes, but this is x transpose y. Okay. Yeah. Okay. Yeah, indeed, you are representing this in terms of the standard basis, and these are the coordinate with respect to the standard basis. Okay. So that brings us to something, that is what happens if we change the basis. How would the dot product look like? Okay. So if we change the basis from the standard basis to some basis B, basis say E1 dot 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 En to some basis B, how is a dot product represented with respect to that? So suppose you have a basis B, okay. What happens to the matrix of the, or well, not matrix. What happens to the representation? I mean, here we have represented it with X transpose Y, and there what do we do? Yes? Which one? This, okay, so you, what conjugate transform of what? Which matrix you are taking conjugate of? X? X is a vector, okay? So you cannot conjugate it. You can multiply it from one side with the matrix. Okay, so that's how the coordinate vectors change. Okay, well, let's come back to it in a moment. Okay, if you think about it by yourself, that's quite good. We'll come back to it in a moment. Okay, before we discuss, I mean, before that, we must discuss what is the matrix of a bilinear form, okay, or the Gram matrix. Or the matrix of a bilinear form. Okay. So let's define it. Suppose you are given a basis of this vector space V. Okay. Let B be a basis of the vector space V. Okay. And let B be given by this V1, V2 to Vn. Okay. So now consider this matrix A, define it as, or maybe we define it by G, okay, because it's a Gram matrix. Okay. So capital G. Okay. This, let's define it as Vi, Vj. Well, now we are taking some bilinear form and we are denoting it by this angular brackets, okay. Need not be a dot product, some bilinear form, okay. And you define the ijth entry by Vi, Vj. That is with respect to the bilinear form, okay. So that's the Gram matrix, and this is actually the underlying matrix of the form given a basis. Okay. So at first, let's see what is the Gram matrix of the dot product with respect to the standard basis. Okay. Yes? This one? Think of this as just S, Vi, Vj, okay? And this is running over I and j, because I mean the rows and the columns.
I comma j represent the ith row and jth column entry, right?
Right.
So the ith row and jth column entry would be the
bilinear, I mean the output in with the bilinear form in the field F. Okay. So yeah, I mean just to give you an idea, an explicit idea what it is, I mean what it exactly looks like, we can compute the Gram matrix of the dot product. Yes, Vishesh. Okay. So let's see. Gram matrix of the dot product with respect to the standard basis. So what is that? Identity, sure. Because how do you define it? This is just Ei, Ej and over Ij, right? That is the dot product of the ith column and the jth column of the identity matrix. That is the standard, I mean, the columns of the identity matrix forms the standard basis, right? Now, this one doesn't give you 1 unless I and j are equal, okay? So, therefore, you get this as 1s on the diagonal and 0s everywhere else, okay? So, the n cross n identity matrix, all right? Now, suppose the base is changed from the standard basis to something else, okay? Well, again, let's postpone thinking about that for just a few minutes, okay? Let's first give you the general setting, okay? So, why the gram matrix is important? I mean, why we define it? Okay. Because suppose you are given some form from V cross V to F, associated with this there exists a gram matrix, right? And suppose your basis is B, some basis B is given to you with respect to which you are defining the gram matrix, okay? So, B is basis of V, and G the gram matrix with respect to the basis B, okay? So, now we will use this gram matrix to represent the bilinear, I mean outputs of the bilinear forms. Okay. So, suppose V is some vector in V and this is given by Bx. Okay. This is the linear combination of the basis vectors which is expressing V. And suppose W is By. Okay. So, what do we do? We would write this using the gram matrix and x and y. Okay. So, note that this one is just Bx By, okay? And recall this is linear in both the arguments, okay? Well, let us write it down explicitly. Okay. So, Bx just means that this is summation of say xi vi, I running from 1 to n, wait a minute, and summation again, well, j running from 1 to n yi, sorry, yj vj. Okay. Okay. So, this vi or vj all are denoting the basis vectors. Here b, well, is v1 dot 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 vn. Okay. I just expanded bx and by in the form, I mean in these sums. And now we will use bilinearity of the form. So, use it and write the expression by yourself. Did you? So, this one is summation I running from 1 to n, summation j running from 1 to n, xi yj vi vj, right? Something seems familiar? This one, right? The ijth entry of the gram matrix. Summation I running from 1 to n, summation j running from 1 to n again, xi. Now, we will write the ijth entry of the gram matrix. So, suppose G is say Gij I j. I will just put Gij instead of Vi Vj. Okay. So this is just Gij Yj, right? And what is this? This is just you are multiplying with the transpose of x from the left, the gram matrix, and here you have the column vector given by y. Okay. So this is nothing but x transpose g y. Okay. Bishesh, you don't seem convinced. So any doubts anywhere? Okay. All right. So this one we just write it as Gij because we defined the gram matrix in that manner. The ijth entry was just the output in the from the bilinear form of Vi and Vj. Okay. So this comes here, and then this is just the matrix the expression for matrix multiplication. Okay. Here you have a row vector, here you have a column vector. You are multiplying it from that side with x, from this side with y. That's all. Okay. So that's how the gram matrix connects with the bilinear form. Okay. So finally we get that VW is equal to x transpose Gy. Okay. So the gram matrix lets you compute the bilinear form explicitly. Well, once you are given a basis. Okay. All right. Yes. We have not proved it for dot product. We said that let's keep the question for a while. We are handling the general case. So this one is not denoting the dot product here. It's denoting a general bilinear form. Okay. Yes. So now let's see if we change the basis from B to some other basis B dash, how this gram matrix changes and how does it affect this expression. Okay. Change of basis. Okay. Not exactly change of basis, but the effect of change of basis on the gram matrix. Okay. So let B dash be another basis of V. Okay. How B dash and B should be related? Yes. Yes. All these things should be linear combinations of the elements of B, and those linear combinations will form a matrix which is invertible because B could also be expressed as a linear combination of the elements of B dash. Okay. So BP, and this is that invertible matrix B. Okay. B is the old basis, B dash is the new basis. You are expressing the old basis in terms of the new basis. You are expressing the new basis in terms of the old basis. Okay. With the columns of this matrix. Okay. Let B dash equal to BP, B another basis of V. Okay. And let G dash be the gram matrix with respect to the basis B dash. Okay. So we'll see how, what is the relation between G dash and G. Okay. So if you remember this question, which we have not answered yet, let's just wipe this part out and proceed. So actually, you see, we are answering this, but in the full generality. Okay. So suppose your vector is v and it was represented as by bx earlier, okay, and now you want to represent it with this new basis b dash and call this x dash. Okay, let's recall the relation between x dash and x, which is given by this expression actually. So this is b p x, and then this one is definitely going to be equal to x dash. This one is going to be equal to x, right? Because a vector v, our vector v is expressed as a unique linear combination of the basis elements in B. Okay. So that is if and only if x is equal to px dash. Okay. So now what we will do, we will write this, well, what we are going to do. We know that VW is x transpose G y, right? And suppose G dash is a new gram matrix. So that would mean that VW with respect to the new basis and the new gram matrix would be x dash transpose G dash y dash, right? And this would be also equal to x transpose G y. Okay. So from this equality, we are going to get a relation between G and G dash. So we will replace this x with px dash. Okay. Let's use this part of the board and replace x with px dash in the last expression, this one. Okay. So that implies that x dash transpose G dash y dash is equal to px dash transpose G py. Okay. Wait a minute. Y should also be py dash instead of y we are writing py dash. Okay, the coordinate with respect to the new basis b dash. Okay, y dash is not written clearly. Wait a minute. Okay. So now what happens? This is x dash transpose p transpose gp y dash. Okay. So you get that x dash transpose g dash y dash is equal to x dash transpose p transpose gp y dash, right? Can we from here say that g dash is equal to this one? Why? Yes, but even then. Perfect. Wonderful. Yes. So instead of x dash and y dash, because this is true for all the coordinate vectors, if we choose the elements of the standard basis, say ei and ej, the ith element and the jth element of the, well, not standard basis, say ith column with 1 at, so we are not talking about basis, now we are talking about the coordinate vectors. So consider the coordinate vector which has 1 at the ith position and 0 everywhere else. That is like ei, yeah, right? And here you have the coordinate vector which has 1 at the jth position, 0 everywhere else. Okay. Now if you take the product of that, what will give, what we will have? So this will be ei transpose g dash ej. So in particular, excuse me, sorry. In particular, we have ei transpose g dash ej, because this x dash y dash were arbitrary. We can put any vectors that we want there. Okay. This would be given by ei transpose p transpose gp Ej, right? Now what will this give? This will give the ijth entry of the matrix G dash, okay? Whereas this will give the ijth entry of this matrix P transpose Gp. Okay. So this is if and only if G dash Ij is equal to P transpose Gp Ij. Okay. So the ijth entry for all I for all j are equal. That would mean that the matrices are equal. Okay. Thus, under a change of basis, the gram matrices are related to one another by, I mean, in this manner. Okay. So, if therefore, if the basis is changed from B to B dash equal to BP, then the gram matrix changes, the new gram matrix is given by G dash defined as P transpose Gp. It's not exactly by conjugation, but by taking the transpose of this matrix. It's, remember, this is an invertible matrix. Okay? And on the right hand side, you are just multiplying with the matrix. Okay? So it's, the form is kind of similar as how the matrix of the linear transformation changes when you change from the basis, but instead of P transpose here, you have P inverse. Okay? Exactly. Yeah. Okay. Yeah. Instead of the P inverse there, you have P transpose here. And note that those may not be always equal. Okay? Unless this is an orthogonal matrix. We'll see those soon. I mean, what we mean by orthogonal matrix, but not for all invertible matrix. This P transpose is going to be its inverse. Which one? Congruent? What? Congruence, or I mean, what do you say? What do you mean by, I mean, congruent? Yeah, you can call them congruent matrices, like we have called the other ones similar matrices. Give them some name, congruent matrices. That's fine. Okay. Yeah. Which one? Xi and yi, we are not taking dot product. We are just multiplying them. These are scalars. X transpose y. Yes. So, yeah, right. So if you have, well, thank you. Let's come back to the question that we asked. That's what you mean, right, Nitish? So earlier we said that how the matrix of the dot product changes if we change the basis, right? So this was a gram matrix of a general bilinear form, and in particular, if we consider dot products, we saw that if V is given by Bx, well, not Bx. At that time, we were considering the standard. Well, you can also denote it by, I mean, call this the standard basis. That's fine, and W as By, where B was given by the standard basis. In particular, the case of dot product. So let's write it down here. The case of dot products. Okay. So we are in such a case, standard basis. Okay. B is the standard basis. We are expressing V and W in terms of the standard basis, and then you are having the dot product of V and W as X transpose Y, right? And now, if you go from B to some other basis B dash, what will happen? This dot product of V and W will be expressed as X transpose P transpose GP, right? Now what is G in identity, right? So it will be just P transpose P Y, okay, for dot products, because G is the identity matrix, right? So if you change the basis by P, so if you go from B to B dash, which is BP, the dot product will change by X transpose P transpose P Y. So this will be the new matrix, which we will call the gram matrix with respect to the new basis. Okay. So now we will discuss what are symmetric or antisymmetric forms. Okay. Not antisymmetric, we call them skew symmetric, sorry. Or skew symmetric forms. Okay. As the name suggests, you can immediately realize what are symmetric forms. So this is symmetric. Symmetric forms, VW would be equal to, yeah? The last part is this one. Okay, B was the standard basis, and you are going from B to B dash, okay, by changing it to some matrix P, okay? And then we know how the, how the matrix of the, the gram matrix changes, right? It changes by P transpose GP, okay? Now, if we started with the dot product and the standard basis, what was G? Identity matrix. So that means G dash should be nothing but P transpose P. Okay. So we were considering the case of dot products, and therefore this G is identity, which lies in between, and you just get P transpose P there. So that's the matrix. Which one? G dash need not be. Take any invertible matrix. If you multiply it with its transpose, is that identity? Not necessarily. Okay. Transpose of P is not necessarily the inverse of P. Yeah. Vishesh. No, actually those matrices for which P transpose P is identity has a name. Okay. Those are called orthogonal matrices. We'll come to them again. But here, in general, P transpose P need not be identity. So that means your dot product with respect to some other basis will have a representation like X transpose, yeah, X dash and Y. Did we have that? This was VW, and this was expressed as X transpose GY, right? Now we said that the G dash. Oh, yeah, sure. Because we are now expressing it with respect to this. Wonderful, yes. We are representing this one, yeah. This is, yeah, sure. Because B dash is a new basis, and we are writing this in terms of the new basis. Thank you, Trishit. Yes, that was a necessary correction. Thanks. Now, let's come back here. So is that point clear to all of you? What we missed there? This is the coordinates with respect to the new basis, right? So this is not going to be the same as x. This is going to be the x dash, because we are now expressing our v in terms of the new basis b dash, okay, and y also in w in terms of also the new basis b dash, and therefore x dash and y dash are the new coordinates, and this is the gram matrix with respect to the new basis. All right. Now, where were we? Yeah, we were just defining what is a symmetric bilinear form. So, what is going to be? WV. Yeah, it's pretty obvious from the definition. I mean, from the word symmetric. Okay, but what is skew symmetric? Minus. Yes. So skew symmetric forms are just VW is equal to minus WV. Yes, Akadeep. Yes. Yes. Well, you are just taking the coordinates. Okay. So what are these? X and Y. These are just coordinates. Okay. So here is also so you are free to choose any set of coordinates. Okay. And here what you are doing, you are just taking a set of coordinate, and here too. Okay. So indeed this is in here, and these ones are also in that basis. Okay. I mean, with respect to B dash. Recall what we had, x dash transpose g dash y dash is equal to x dash transpose this new matrix y dash. Okay. Now you are choosing x dash as EI and y dash as EJ. That's all. Okay. So have you seen examples of symmetric and skew symmetric forms? Yes, indeed. So this is just the determinant. Okay. Switch the rows of the determinant, and your determinant is multiplied with a negative sign. Okay. Whereas this one, what is an example of that? The dot product. Okay. So example, dot product. Here example, determinant of 2 cross 2 matrices. Okay. Okay. Now let's clear up some part. Now we are going to prove a brief proposition, that is, a form is symmetric if and only if its gram matrix is symmetric. Okay. And then leave something for you as a homework. A form is skew symmetric if and only if. Complete it. Its matrix is skew symmetric, right? Okay. So here is the proposition. Okay. Suppose your form is symmetric. Okay. So let's write it down at first. A form, a bilinear form, I mean, is symmetric if and only if so is its gram matrix with respect to some basis. Some basis. Okay. That means if it has a symmetric representation with respect to some basis, it will have a symmetric matrix with respect to any other basis. Okay. So proof. How should we proceed? Right. Vi comma Vj is equal to Vj comma Vi, as the form is symmetric. That means the ijth entry of the matrix, gram matrix, is equal to the jth entry, and that means what? that if you take the transpose of this, what do you get? You get G back. Okay. And actually, this is an if and only if thing, right? So the other way it's also the same. Right? So this is actually the proof. Okay. And in particular, that means it doesn't matter which basis you are taking. If the form is symmetric, the matrix, the gram matrix is always a symmetric matrix. Okay. Well, and the other part is also exactly the same. That would mean that Vi Vj is minus Vj Vi, and so G transpose is minus G. Okay, we do not have to do much now, but we can, I mean, time to do much now, but we can define what are positive definite and positive semi-definite, or negative definite, negative semi-definite forms, and also what is an indefinite form. Okay. Positive definite or positive, okay, this is the first time we are writing the definition, so maybe I write the full form at least for once. Positive definite or positive semi-definite or, okay, so this is one type of form, this is negative definite or negative semi-definite, and third is indefinite forms. Okay. Okay, here also forms, and forms. Okay. So what does it mean by a positive definite form? The first one, well, you take some vector which is a non-zero vector, you take the product with itself, well, you are putting the same vector in both of the arguments. If that is greater than 0, always, we say the form to be positive definite. Okay. So first one, V in V minus 0, then V is greater than 0. Okay. By the way, can you tell me what is this for any bilinear form? Why? Yeah, you can just represent the coordinate. Yes, but just from bilinearity, you don't even have to go to basis. Okay, you can write 0 as 0 plus 0. Okay, and then this will be just sum of two of them. Okay, and you get from there that this is just going to be 0. Okay. And so for 0, you are getting this to be 0 for all, I mean, for over all vector spaces and over any for any bilinear form. Whereas if your bilinear form is like that, that this is greater than 0, we say the form is positive definite or positive semi-definite. Okay. And well, actually these are more specialization over the symmetric forms. So here given a symmetric form, we call it this one. So we call it positive definite or positive semi-definite. Well, positive definite if this is strictly greater than 0, and positive semi-definite if VV is greater than equal to 0. Okay. So negative definite and negative semi-definite are kind of similar, right? You can understand that you are taking again v here, v minus 0, and then v for a negative definite form, this is going to be strictly less than 0. Whereas when it is negative semi-definite, then v is going to be less than or equal to 0, okay, for non-zero thing, I mean non-zero vectors in here. Okay. And then an indefinite form is that you cannot say exactly whether this is greater than 0 or less than 0 for all the things. Okay. For example, there is something called Lorentz form. Okay. You have seen Lorentz transformations and Lorentz forms already in special relativity, or you haven't. Okay. So you have this matrix, say A is 1, 1, 1, and minus 1. Okay. So corresponding to the space coordinates and the time coordinate there. Okay. Consider this to be your Gram matrix. Okay. And of course, it's a symmetric one, but this will give you indefinite form. Okay. So this is the Lorentz form. So example of an indefinite form. The Lorentz form, okay, whose Gram matrix with respect to standard basis is given by this one. Yeah.
When we talk about definiteness, should the field be necessarily real?
Well, actually, for the moment, we will talk because we are now considering this greater than or less than things. So, indeed, I mean, we will talk about symmetric positive definite forms only over the real vector spaces. Okay. For complex vector space, we will generalize this a little bit towards complex, because these ones, well, complex, but this should give always the real values. Otherwise, you cannot say that greater than or less than. So those will be called Hermitian forms. We'll see all of them later. Yeah, please. Okay. So that's all for today's class. See you again on Thursday.